Hello, 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 and welcome to your AP Chemistry review video. So this review video is really going to be focused on electron configurations, orbital diagrams, and some of the basic terms you learned last year in writing these electron configurations. One thing that you used in regular chemistry was probably Aufbau's order. Looked kind of like this image you see here, and it was used to do orbital diagrams. I am going to hop into the notes to show you where this is in the notes in a couple minutes, but for right now, let's just stroll down memory lane. So your teacher would probably say, hey, why don't you write the electron configuration for an element? And then you would look up the element. Let's say that element was calcium. So you find calcium, and calcium has 20 electrons, and your job was to write down all of the energy levels, sub-levels that electrons would be in, and then how many would be in each. That's what you were doing when you were writing out like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And you would use Aufbau's order by saying, okay, these 20 electrons all need to have a home. You start at the top and you place the first 2 electrons, and you'd slide down and do the next 2. 6 more, 2 more, 6 more. Look, it's kind of in a weird order. 4s2 came after the 3p6. It was out of order, but that's why we had Aufbau's order, so we could figure out what order it was in. And these superscripts, 2 plus 2 plus 6 plus 2 plus 6 plus 2, should add up to 20. If you add all the superscripts together, they add up to the number of electrons that element had. And we would write out really long electron configurations. Remember that? Sure you do. If you don't, you need to kind of go back and look at some of those questions from years past. But the problem is, in AP, you're not going to be given Aufbau's order. You're going to be given a periodic table. So this order, some people just like went, this order is actually on the periodic table. It's right in front of you. Let's look at one periodic table that has them written on it, so it's kind of like cheating. But look, here's calcium right there. 4s2, that's the last piece. The periodic table is organized by S orbitals, P orbitals, S sublevel, P sublevel, D sublevel, and F sublevel in blocks. Like all of the elements in this zone of the periodic table have S's as their last piece, and you could see it real. If you look, I can zoom in. You probably can't see it unless your screen is really big. You look, S, 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 and you can even see these are all 3s1, 4s1, 5s1, 6s1, and then the other columns, s2, 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 s2. All right. What about in the middle? You can see here are D, 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 D. On across to the other side. Here we have the P area. This whole area here is where things end with P. And so the periodic table is actually organized by the S area over here, the P area over here on the right, where we have the P sublevel elements, as in elements that end with P in the last piece. In the middle, we have the D. One thing you have to remember about the D, though, is that they are off by 1. So you've got 4 S's, and then these are all 3 D's. 5 S's, and these are all 4 D's. They're always off by 1, which is the bad joke I usually make about Aufbau's order, made things off by 1 or off by 2 or something like that. And then the F's were down here. We don't really ever use the F's, but that's where they are. If you look a little too closely on this periodic table, you'll see a bunch of exceptions, which you don't need to know. They exist, but we don't need to know them. So I'm not even going to point them out. If you want to go find exceptions, you can, but you don't need to know them. This periodic table really breaks it apart nicely so that you can kind of see where each energy level is and make it much easier. So you could even find a specific element and figure out what the very last piece was. So say we were looking for this element. Why is this element's last piece 6p2? Well, first it's in the p area, and it's 1, 2, 3, 4, 5, 6 energy levels down. N is for energy. 6 energy levels down. And then everything in here is P1. Everything in here is P2. On down. P3, P4, P5. And the noble gases are all P6. So we can easily figure out this element, which is lead. Is that lead? Yeah, that's lead. Lead's last piece is 6p2. And if we wanted to write its entire configuration, which would be really painful, we'd start with the 1s's. There can be 2 of them. Then we go to the 2s's, 2p, 3s2. And I just keep going across. Ooh, okay, now we're going to go through the 4. There'll be 3p6. That line is done. Go to the next line. 4s, 2, 3d. Remember, they're off. 4p. There's a whole bunch more. Then you would end up right before the 6p, and you'd get your way all the way there. You just keep working the order until you get there. Let's try one that's not lead. That's like normal. Let's try bromine. So bromine has 35 electrons, and on a periodic table, bromine would be found right here. It's the 4th level down in the p areas, and it's 5 over. So the very last piece would be 4p5. 4 energy levels down, or 4 energy levels worth of electrons. The last one is in the p sublevel, and there are 5 in those p sublevels. So this is your ending. It always starts with the same beginning, 1s2, and then 2s2, and then 2p6, 3s2, 3p6, 4s2. The d's are off by 1, so this is a 3d10, 10, 4p5. You will often, so that's a configuration. That shows every electron in bromine assigned a space. There are electrons on the 3rd energy level and an s sublevel. Yep, there's 2 of them, etc., etc., etc. Sometimes you'll see these written the other way around. That is not the order in which they fill. If they are written this way, then that's just to represent the energy levels in the proper energy order, not in the order in which they fill. So if they wrote 1s2, 3p3, 3d10, 5s2, the 4s2 actually fills up first, and then the 3d10, but these guys are all 3rd energy level, so they're often grouped together. And these are 4th energy level, so they're grouped together. You might see it either way. Those are considered both to be, dang, bell. Alright, I'm not going to go back and delete dang bell. That's just going to have to be in there. Hope you had a good chuckle about that. Another thing we did a lot was noble gas configurations. That really simplified things. You always went to the previous noble gas, previous meaning the one that comes before it. So if bromine is most closely related to whatever noble gas this is, it always has to be a noble gas on the previous energy level. That noble gas for bromine would be argon. So we put argon in brackets, and argon is 1s2, 2s2, 2p6, 3s2, 3p6. And then we just have to write the pieces that come after argon that make bromine look a little bit different. Okay, so that was a lot what we learned last year. Now let's actually look at your notes. We're going to go over the first couple sections in class. Let's see here. Where are we? I want to go to 7.7. So 7.7 is kind of the same idea. It's about orbital shapes, energies, electron spin, Pauli exclusion principle, polyelectronic atoms, and then the history of the periodic table a little bit. So you often see this notation, for different symbols. You might see 4s1 or 5f, 7 or something. And the number in the front is the energy level that we're just talking about. The letters S, P, D, or F are the 4 different sub-levels we're allowed to use. There are more, but we only use S, P, D, and F. And then the superscript is the number of electrons that are put into that sub-level. And the number of electrons that could fit in a sub-level depend on how many orbitals a sub-level has. So let's see, S, P, D, F. The S only has 1 orbital, and an orbital can only hold 2 electrons. And we represent electrons with these little arrows. The P's have 3 orbitals, and they can each hold 2 electrons. So therefore we're at 6. The D's can hold 5, and I'm going to cheat and make it like this. That's 5 boxes. And then you would have 10 arrows, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the F's can have 7 orbitals. There we go. So 1 orbital, 3 orbitals, 5 orbitals, 7 orbitals. Oops, that's not the number 7, that's the number 6. Odd numbers. Odd numbers, 1, 3, 5, 7, multiplied by 2, can hold 2 electrons, 6 electrons, can hold 10 electrons, can hold 14 electrons. Of course, these electrons aren't actually moving in boxes. They aren't actually held in cute little boxes. That's just a representation or model of where the electrons are, because drawing the different shapes of the orbitals is a gigantic pain. So the sublevels get divided up into these orbitals and all have different shapes. The only shapes that are easy to envision are the S, which is a sphere, and the P orbital. Here's one P orbital. A P orbital kind of looks like a peanut, and centered right in the middle of that P orbital, X, Y, Z axis, right in the middle would be the nucleus of the atom, and the electrons are moving on the surface of that peanut, or darn close to the surface of that peanut, within a range and tolerance. There can be up to 3 p orbitals, which is why I was making 3 boxes, and the difference really between them is the axes they're on. So this one appears to be on the x-axis. You could also have one on the y-axis. That's not very beautiful. And then you could also have one on the z-axis. This one looks like it's going back. This one's coming out of the board. That's a little over-exaggerated. So the p orbitals look like 3 different lobes, 3 different pairs of lobes on the axes. The d orbitals have really different shapes. It's actually 4 pairs of lobes per orbital. No one really tries to draw them. You can find a diagram in your textbook that shows like weird little flower shapes. Like that is one of the d orbitals, and it's on none of the axes. And there's 5 different weird-looking clover-like shapes. Each shape is one of the orbitals. Again, no one ever draws them or asks questions about them, but they do pick at pictures of them every once in a while. The real difference, though, is that why is there suddenly, this d orbital when there wasn't? So, if you think about what we're doing here, here is our axes. I'm going to zoom in, like really zoom in here for a second. That was pretty extreme. So in the middle is a nucleus, and then around the nucleus is a sphere of electrons, and this is the 1s orbital. It's a very tiny sphere. Let me see if I can write 1s. All right, 1s. just so close. All right. And then if you move out further, you have a larger sphere on the second energy level, and it's the 2s. And then on about the same distance, you have the 2p, which here's one of them on the x-axis. Here's another one. And now I need to actually add a z-axis. So this is the z-axis going back and forth. And so the third p orbital, all right, there we go. That actually doesn't look half bad. Doesn't look half good either, though. So there's your 1s, your 2s, and then these guys are the 2p's. Well, there's not much space in between these lobes. Let's zoom out, though. Oh, where'd it go? There it is, look! So as we zoom out, orbitals, as we zoom out, we get to the third energy level, which is a larger sphere. And then there's a 3p, a 3p, a 3p, a 3p. And the space in between these p orbitals starts to really grow. There's much more distance. And according to Aufbau's order, the next thing to fill in, it goes out of order here for a second. Let me see, pick a color that will work. We'll go red. So the next thing is actually the 4s. You can put 2 electrons in that giant sphere. And then come back in here, and this zone, these zones here, you know, can be filled in with those funky looking d orbital shapes. And it's really getting hard to visualize now because it's a three-dimensional shape, lots of electrons moving around. At this point, we're at least at 21 electrons, and they're all moving on these different shapes. There'd be electrons moving, electrons moving, electrons moving, electrons moving, there'd be lots of electrons moving. But so let's answer this question. Why doesn't the 2d orbital exist? It's a space issue. There's not enough space on the second energy level. These electrons, there's not enough space between the 2p's to fit in another pair of orbitals in there. So if you've been ever written these orbital diagrams, 1s2, 2s2, if you've been writing these and you didn't really understand what you were writing, you were basically describing the shapes upon which electrons are moving. A really small sphere holds 2 electrons. A larger sphere holds 2 electrons. And we're kind of just describing how they move around. I like to talk about that. We don't usually get any questions, ever, where you would draw. In fact, you will never draw this shape. Ever. This drawing is just for understanding purposes of what the heck is going on. It's not for actual questions. All right, this one's an easy one. What is ground state? This means that there's no extra energy. No extra energy. So all of the electrons are pulled in as close as possible. For instance, for hydrogen, hydrogen's usually 1s1. Let's change to blue. Oh man, orange and blue, that's ugly. Who would put orange and blue together? So the first energy level, there's an s orbital that holds 1 electron. If that 1 electron was excited, meaning it had extra energy, it might get bumped to a higher energy. It could be 6p1. You know, that's a huge energy difference from the first to the 6th energy level. So when electrons are excited, they have to go to a higher energy level. That's empty. So if you were talking about, what did I draw here? This is, I think, neon, 1s2, 2s2, 2p6. If one of the electrons here got excited, you could have 1s1, 2s2, 2p6, 5p1. And one of these electrons was excited, meaning energy was added to the electron and it was too much energy for this low state. and that energy bumped that one up. There are like probably 50 or 60 different possible empty spots not being used that it could jump into. And because when they jump out there, there's no competition, it's not going to be perfect once they hop out to like the higher energy levels. Whereas when it's in the ground state, the only way for them to exist in the ground state is to all fill in perfectly. Alrighty. Magnetic spin, we talk about how electrons are moving. They're kind of like moving magnets, but the magnet only has a negative side. And for the two electrons to exist in the same orbital, they have to have opposite spin. This is what the Pauli exclusion principle is all about. Star, star, star. Make sure you know who the Pauli exclusion principle is. It's the guy that says you must, it excludes same spin within an orbital. Because if you have two electrons in the same orbital moving with the same spin, they'll end up pushing each other right out of the orbital and kind of canceling out the existence of each other. So, wait, what is the consequence regarding the number? The Pauli exclusion principle also says that they can't have more than two. So you'll only ever see an orbital with two electrons. They'll always have opposite spin. If there's more than two electrons, you need another orbital. Once you fill up an entire sublevel, say the 3p sublevel, say that was filled all the way up. If you have more than 6 electrons for the 3p, you need to go to the next sublevel and have a new orbital. If each orbital can hold a maximum of 2 electrons of opposite spin, how many electrons can each of the following sublevels hold? S's always have 1 orbital. 2. P's always have 3 orbitals, and I'm just drawing the orbitals vertically instead of left to right because I don't have space to make all of them. Oop, that's an F, so it needs to have, those are 7 really ugly looking boxes. 1, 2, 3, 4, 5, 6, 7. Each one could hold 2. So you could put 14 electrons in those 7 orbitals. D's have 5. So that would be 10 electrons. And then D's still have 5, so the 4D can also only hold 10. So this is how many can be in the sublevel. Each, the S, P, D, and F sublevel, each have multiple orbitals. If the question was how many electrons can be in a 4D orbital, how many electrons can be in a single 4D orbital? They can only hold 2. An orbital can only hold 2. The sublevel could hold 10, but one orbital inside the sublevel can only hold 2. What else do we have? This is actually, we'll talk about this in class. Skip this, we'll come back to this. It's pretty easy, but we'll skip it if we didn't learn it last year. Mendeleev, what was he looking at with the periodic table? Mendeleev was looking at periodic trends, when did things repeat, and he was focused on the mass. So he was focused on the repeating trends that occurred from time to time or periodically, and he was focused on the mass of the elements. Properties he looked at were things like density, types of molecules and ionic compounds they formed, boiling points, freezing points. He really looked at lots of trends and looked for patterns within them. Let's see, several atoms of element 116 have been observed. If they were not radioactive, what properties would you predict for this element? Well, where would 116 be? Let's go find a periodic table. I think there was one at the very beginning. So 116 would be right there. 116 would be in the oxygen family. So you would expect element un-un-hexium, 116. One more. You would expect it to have a charge of like a -2. because it's in the oxygen family, and then you would expect it to make bonds like oxygen, like there'd be H2X, just like there's H2O, and it would have a lot of the similar properties. You'd see similar boiling points and melting points for it, based off of what you see in there. The modern periodic table is not based on mass, it's based off of atomic number. And I believe that was Henry Moseley. I hate saying things in record that I'm not positive about. I'm pretty sure it was Henry Moseley that reorganized it by atomic number. Then only fixed a couple spots, like iodine and tellurium were backwards on a periodic table here or there. Nickel and cobalt were backwards because the masses of the isotopes kind of put them out of order. And Mendeleev's periodic table is more focused on mass. Atomic number, aka atomic number, is also number of protons. So I didn't really know anything about protons when Mendeleev created the periodic table. Mendeleev. Off-Boas order, electrons always fill from the lowest to highest using off-Boas order. The Paul exclusion principle, we talked about that. Orbitals can only hold 2 electrons. They have to have opposite spin. You must know how many electrons each we have by each quantum number. Hund's rule. So Hund's rule is the one that says, let's draw, let's say we're doing 3, that doesn't look anything like a 3. Try again. 3p4. Well, we would put 1 electron in each orbital before the opposite spin one. So you spread them out within the sublevel to each orbital before you double them up. Some kids don't get that, so I always like to remind them we're talking about negatively charged electrons. 4 negatively charged electrons who are going to repel each other as far away as they possibly can. And each of these boxes represents one of these orbitals from this horrible drawing I have here. And so those electrons are going to try to move to the farthest possible distances apart. The p's, they would be in these 3 orbitals that I kind of just slashed with the purple, and they'd be as far away as possible within those p's. It would be 3 separate orbitals then to get them really far apart. The fourth one, though, is forced to share an orbital. And if it's going to be in the same orbital, it has to have opposite spin. But Hund's rule is really about spreading them out into separate or degenerate orbitals. Degenerate just means there's all the same energy, but they're spread out in this case. It's not like, Billy's a degenerate or something like that. It's that there's several orbitals of the same energy value, so we need to spread them out. This says you must memorize off-Boas order or understand its arrangement on the periodic table. That's really the easiest way. Again, I was talking earlier about how there's S's and D's and P's on the periodic table, and then the F orbitals are down here. If you really understand how the periodic table is put together, you don't have to memorize it. So again, here is off-Boas order and how the periodic table is put together. You have this in your notes. This is really what you want to kind of see inside your head when you look at the periodic table. So you can find an element like boron here, and you can go 1s2, 2p. Ooh, already messed it up. Nice job. Who's the teacher here? 2s2, 2p1 as you get to that spot. So you say 1 s's, then the 2 s's, and you only have one of the p's. Where's vanadium? Vanadium is right there. Be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 3d3. And again, if after you've written it, you decide to swap these 2 around, ooh, that looks nasty. If you want to swap these 2 with each other spot-wise, now it looks like a happy face. That's fine. After you've written it correctly, a lot of people swap the fourth one and the third one around so that all the 3s are together and all the 4s are together. Shorthand or noble gas configuration and number 23. So let's see, we were doing boron and vanadium. Boron, really, this one doesn't save us much. Helium would be the noble gas before it. For vanadium, though, vanadium, we do get to save quite a bit of writing. Argon's the noble gas that comes before it. Let's see, let's try a couple more. Strontium. Strontium, we would only have to write, well, it's just like krypton, except it's got that 5s2 also. Molybdenum, where is Mo? Mo is also krypton. 4s2, no. 5s2, 4d. Molybdenum is 4 elements over, so we're going to say 4d4. Molybdenum is actually one of those, never mind. Germanium, argon, and then you got to build to there. So 4s2, 3d10, 4p2, which makes sense. It's underneath silicon and carbon, so it's a p2. Element 111 would be right underneath gold. So first say radon, and then 7s2. Time to go down to the 5f's. 5f14, 6d, not 10, 6d and 9 would be where it is. Here's a good question. Which electrons are not included in the noble gas configuration? The core electrons. We don't worry about the core electrons. So when we've written, argon here, all of those electrons that argon represents are the core electrons. Core electrons are on the inside. So you have all these electrons around the nucleus, and then you have the outside. And the outside electrons are really the only electrons that interact with other atoms. So those are the ones we focus on. So these guys are the outside electrons, and we call the outer electrons the valence electrons. So only the outside ones really matter in reactions. Oh, and we're done. So make sure you know how to do electron configurations, noble gas configurations, in super simple orbital diagrams. Orbital.